Minutes on that video, that's not good. Okay.
That's not okay. Why did you ask Nelson?
Okay, anyhow.
We got until like 1:15. We got 17 minutes. Oh,
The what?
1:15.
You're right.
I had no idea. I didn't even know what that means.
1:15?
He said we have to 1:15. I didn't know.
I don't think so.
Oh, I have no idea.
It's alright.
I just know I'm supposed to be at 12.
So that would give us-
an hour late. I thought everything was backed up an hour.
No, it changes.
Wouldn't it be moved forward?
You know, we correct.
Instead of backed up
Oh,
an hour.
shut up.
A class normally goes for an hour and a quarter.
Right.
Yeah.
If we reduce that to an hour between classes, it might be 1:05.
Yeah, I'm gonna.
Let's see, we gotta compress 8 hours into 6 hours. That's 3/4 of the time, right?
Right.
And we normally have 90 minutes between classes, right? And 3/4 of 90 is 77.5.
We get out at 1:10.
That's what I just said.
Technology.
And he just, now that's what he just said.
He
Okay.
said- Sorry.
Okay, well, you're welcome to sit back and enjoy. If you need to get up and wander out, you're not trapped, even though you might feel like it being back there. Okay? So you're fine. Okay. Well, I'm glad we got an extra 15 minutes. Now, where'd my calculation go wrong? How can we get out at 1:10? I'm not.
But see, we didn't start until 12:10. So it just made it an hour, right?
I thought we started at 12:05.
No, we started.
No, we started at 12:10.
Okay, that worked. That does it. You know, sort of. Well, 3/4 of 75 is not 60, so I'm still. I don't want to think about it. Okay, now, that doesn't feel quite right, but whenever people show up and you guys get tired, we'll start the next class. Okay. Now, okay, here's our, pressure, force per unit area, right? So our picture is, we've got this chunk of water here.
Wait, isn't that force per unit area squared?
Nope.
Per unit.
Oh,
When you
per unit
square,
area. My bad,
yeah,
my bad.
area is in square units.
My bad.
When you do square inches, that's
My bad.
that's an area. Okay, so here's our increment of water, right? Delta X and AX, but here's our force. Now, since I've got, what, 11 minutes, I can digress just a little bit and say, well, really on this thing, this is not the only force acting on it, but this is the direction the force produced by pressure will act on the cross-sectional end of the thing, okay? Of the increment. We also have forces acting down and up, and actually they're, yeah, we got pressure acting down, we got pressure acting up, right? What's greater, the pressure here or the pressure here?
Oh, up.
Wrong. What's greater, the pressure here or the pressure here?
They're equal.
What? No, wrong. What's greater, the pressure here or the pressure here?
Let's go bottom.
Yeah, you only have one alternative. Okay. Now, okay. So, what? The deeper you go, the more pressure, right?
Right.
Anybody ever been in a swimming pool?
Yeah.
Oh, yeah. That makes sense.
If you know how to swim, you've probably done the common thing and see how deep you can go, right? And pretty soon your ears start to notice. Okay, pressure's increasing. Now there are reasons for that, and we'll talk about those. Right now I want to talk about the energy relationships, and we'll wave our hands over a couple of the essential ideas, and we'll
So
fill those
is the
in.
pressure down more or pressure up more?
Oh, pressure acts in every direction.
I know, but on that, is it down or up?
Well, pressure acting on the bottom of this thing is up.
Yeah. Is that
Pressure acting on the top is down.
So you're saying the one acting up is greater, right?
Well, it's deeper. Has to be greater. pressure acts normal to the surface. And y'all, from what I've ever with calculus, know exactly what that means. And if I gave you a quadratic surface and asked you to calculate the normal vector, you'd be able to do it very quickly, right?
Right.
Maybe not that quickly, but you know what to do. You know what it means. Okay? And in some cases, I think you could calculate it quickly. So we have the pressure acting all the way around, but more on the lower half than on the upper half, right? Okay? That's where the buoyant force comes from. Okay? More pressure under than upward. Right?
Right.
Okay? But on okay. We're assuming this is a small exit hole. So there's not much difference here. So we're just going to say, well, yeah, this is the net force. There's actually a little bit of an upward component to it, but it's so small compared to this that we can't really even see it. Okay? Although it's what keeps the water from sinking while it's in the container. And we'll talk more about that, okay, next time. Okay, so if the net force is in this direction, then it's safe to say that F delta X is just F times delta X, right? Okay. Now, there's your net force. What's the pressure on the end here?
F net divided by AX.
Yeah. So pressure is F net over ACS, which is what?
Pascal? Oh, you mean? So wait,
Okay, so that's really.
I mean, it's just that, but
Yeah.
Hold on. What is our?
it doesn't.
No, that's not
It doesn't simplify.
Can't.
That's just it.
It's just that.
Oh, whoa, it's not ACS.
Okay.
I probably misled you.
Oh, AX.
Because we don't have nothing for that.
Sorry.
Okay, then
I mean, that is the cross section.
Rho GY.
Rho G.
Yeah, rho GY.
Yeah, very good. It was my fault, sorry.
Hey there.
Okay?
What's the, how do you write
Well,
One nickel, one
What's the symbol for
PA.
Oh, that's what
It's just lowercase PA.
lowercase p?
what we've just established is V exit is the square root of 2GY. And if Y is measured from here, the pressure down here is rho GY. That make sense? Well, that's 2/3 of Bernoulli's equation. Now, I mentioned I went to a fraternity reunion in mid-September, okay? And I remember Pete Durakowitz, metallurgy major. I had a great career as a metallurgist, metallurgical engineer. Very smart guy. And he was talking about sitting down with a couple other guys, and I'll remember, The names don't matter at this point. So I won't, mention them. I just mentioned old Pete. He's retired now, as most sane people my age are. And he said, we're sitting down, I remember so-and-so was just really good with all that Bernoulli's equation stuff. We'd sit there brainstorming this stuff until we finally understood it, okay? So Bernoulli's equation is kind of a big deal. So I want to, and not because of Pete, because I always do. I want to start off. We got this much of Bernoulli's equation, okay? And Bernoulli's equation just says this. For continuous fluid, this plus this plus this is constant. Okay? Now we've got our rho gy here, and it's related to pressure. I've talked a little bit about why. And the square root of 2 gy. Okay? If we do 1/2, well, that's related directly to the kinetic energy to this, okay? That's a kinetic energy related term, okay? That's a force pushing it out related term, and that's pressure, okay? That's Bernoulli's equation. Nothing too intimidating, because it's pretty easy to understand
That makes
how those things are related to energy, right? This one and this one especially. That's just like potential energy, and that's like kinetic energy, except you're using rho, right? And if you multiply this by a volume, well, then you do get a kinetic energy and a potential energy, right?
We
Okay.
use that in differential equations, didn't we? Bernoulli's.
Yeah, I mean, I had you, well, actually, I think in multivariable calculus, I asked you to do the differential of this expression, okay? I don't think we actually did a differential equation, but the differential equation that we did, since you mentioned it, okay, is just this. The velocity up here is what? It's Vx is divided by, well, times this cross-sectional area divided by this one.